Hi, everyone, and welcome to Stats with Andrew. Today, we're going to be looking at simple linear regression in Genstat. So let's get cracking. This is how Genstat welcomes you. The formal way to open a file, if you're trying to find it, you might not have opened it for a while, is File, Open, and you follow the directory structure. But if you have used it recently, it appears down here in the recently used files, and our file is this top one, age versus BMI. .xlsx, so that's an Excel file. And it also appears here at the welcome screen. So let's just double click that. We get S:*Genstat. So S means sheet. And normally in an Excel file, you probably have quite a few sheets. And you would search through this window to find the sheet that you wish to use. And I just have a habit of always labeling it Genstat, the one I wish to use. And here I haven't got any other sheets. I'm just being nice and neat. We don't need to click next and go through the various importing options because it's all set up correctly. We've got 2 columns and 1 header row. So it's all set up and ready to go. So we just hit finish. Okay, here are our data. Age versus BMI, body mass index. If we go to Windows output, we can just see how the data have been imported. It's just telling us that for age, there are 24 values and 0 missing values, and it gives us the minimum, the maximum, and the mean. And likewise for BMI. So it's good to know we've got no missing values. In a very large data set, sometimes you might accidentally have missing values, or you might very well have missing values that you are aware of, and your analysis can actually accommodate them. Okay. So we will now run our simple linear regression. And to do that, we go to the Stats menu, Regression Analysis, and the very top one is called Linear Models. And below that, a whole lot of other regression modeling options, mostly various nonlinear models. Now, even within linear regression, there's many options other than just simple linear regression. So that's come up here as the default. But there's, say, multiple linear regression, which I've used before, and it's quite a powerful technique. But there's also polynomial methods and various other things. We just want to keep this as simple linear regression. Okay, so our response variate is BMI, and our explanatory variate is age. That's because BMI responds, or at least has the potential to respond, to age, whereas age does not respond to BMI. Age is determined by the ticking of the clock. It's not determined by your BMI. Similarly, the other way to look at it, looking at the second term here, explanatory, age has the potential to explain BMI, but BMI does not have the potential to explain age, okay? It's not influencing your age. Now, the other terminology that's used in other stats packages is dependent and independent. So our explanatory or X variable is, the X is always the explanatory and the Y is always the response. So the explanatory or X variable is our independent variable because, as I just explained, age is independent of BMI. It just keeps going along with the ticking of the clock. And then BMI, conversely, is dependent because it at least has the possibility to be dependent upon age. It could be dependent upon many other things too, like diet, etc. But it has the possibility to be dependent upon age. It makes logical sense. Okay, we'll go to options and just select plot residuals, just so we can see whether our assumptions around stability of variances are being met. And we hit run. Now this brings up another screen, which you won't be able to see yet. So I'm just going to have to switch the screen share, sorry. And I'll be back, here it is. Now we can see here that the residuals, the spread of the residuals, so this way, the spread is similar as the mean increases. There's one outlier here. So we've met our assumption of homogeneity of variances. Now, you may wish to do a more formal test. Those who use SPSS will be familiar with Levine's test for homogeneity of variances. It's used as a default in many statistical analyses. Or you can just look at a plot like this. Our normal plot and our half normal plot, there's some divergence from normality there, but it's nothing too extreme. And the assumptions of the assumption of normality is not as important as the assumption of the homogeneity of variances, because regression and ANOVA are actually reasonably robust to departures from normality. So we're not going to worry about that. I'll just switch back to the other screen. Give me a sec. Okay, we're back. So we've got a dashed line denoting a new analysis. So regression analysis, and here is what we might call our ANOVA table. And for our regression, it is highly significant. So the p-value, or the F probability, is less than 0.001. So we have a highly significant relationship, and that's probably not surprising. Then we have down here, percentage of variance accounted for. Now, you might think, oh, that's effectively the R-squared value, but R-squared is scaled from 0 to 1, so 0.795. That's almost the case. It's actually the adjusted R-squared value there. So the adjusted R-squared is 0.0795. Now, if you, again, are used to SPSS, you'll see that R-squared is reported and then adjusted R-squared. And that's because, depending on the circumstances, there's a degree of bias in the estimation of R-squared, and it tends to overestimate the goodness of fit. Okay, so that's the adjusted R-squared there. Then we have to think, well, we need to be able to present an equation for our model, for our straight line. So going back to school, the equation for a straight line is y equals mx plus c. In more statistical speak, we have a function of x equals ax plus b. It's the same thing, just use the mx plus c nomenclature for the time being. M is the gradient and c is the y-intercept. So here we have our y-intercept of 5.44. So that's it there. This constant here is our y-intercept. So this is very important to know. And our age, on this age line, sorry, we get this value 0.6258. That is our gradient. So that means our equation for the straight lines is y, or our y value is BMI, body mass index. BMI equals 0.6258 by x, which is age, plus 5.44, which is the y-intercept. So that's very important to know. So now you can actually put the equation together. You can present the adjusted R-squared value and the overall significance of the relationship. So I hope that's helpful. Good luck running simple linear regressions. For those who use SPSS as well, keep an eye out for the sister video I've done for simple linear regression in SPSS. Okay, thanks for listening, and I'll catch you next time. Bye.